Namaste and welcome back to JEE Physics with Typical Monk. This is class 17, current electricity. A wire looks still, but inside it, a river of electrons drifts along, nudged by a field. Give that river a push, an EMA, and it flows through resistors, splits at junctions, and charges a capacitor at its own measured pace. Today, we read Ohm's law from the inside, balance a Wheatstone bridge, weigh a cell's internal resistance, and watch a capacitor fill along an exponential curve, one idea at a time. Here is what you will learn today. First, drift velocity and Ohm's law, and resistivity. Second, series and parallel resistors and Kirchhoff's laws. Third, the Wheatstone bridge and the meter bridge. Fourth, cells, EMF, internal resistance, and terminal voltage. And fifth, the charging and discharging of a capacitor through a resistor, plus the drills. One idea at a time. 4 ideas. Run this entire chapter. Look at them together first. Ohm's law. B equals IR. And, from inside, the current I equals NEA times the drift velocity, the electrons creeping along under the field. Resistance. R equals rho L over a longer or thinner means more resistance, and for a metal, rho rises with temperature. Kirchhoff's laws. The junction rule from the conservation of charge and the loop rule from the conservation of energy. And the time constant. Tau equals RC, the pace at which a capacitor charges to a resistor. Now look at the picture. The Wheatstone bridge, the classic way to measure an unknown resistance. The bridge. 4 resistors, P, Q, R, and S, arranged in a diamond, a galvanometer bridging the middle, and a cell across the far ends. Balance. The bridge is said to be balanced when no current at all flows through the galvanometer. The needle reads 0. The condition, at balance, P over Q equals R over S. So if 3 resistors are known, the fourth, the unknown, follows at once. And the meter bridge. It is a practical Wheatstone bridge built on a 1-meter wire. The balance point along the wire gives the ratio directly. Now the working formulas, the ones the exam turns into marks. The ribbon holds the anchors, Ohm's law, resistance, and the time constant. Series and parallel. In series, the resistances simply add. In parallel, the reciprocals add 1 over R equals 1 over R1 plus 1 over R2. The junction rule. The sum of the currents flowing into a node equals the sum flowing out of it. Charge is conserved. The loop rule. Around any closed loop, the sum of the EMFs equals the sum of the IR drops. Energy is conserved. And cells. The terminal voltage B equals the EMF minus I times R on load. It is always a little less than the EMF. Let us work the G favorite, a cell under load. A cell of EMF 6 volts, an internal resistance 1 ohm drives an external resistance of 2 ohms. Find the current, the terminal voltage, and the power. In the circuit, the EMF is 6 volts, the internal resistance R is 1 ohm, and the external R is 2 ohms. The current, I equals the EMF over, bracket R plus R, which is 6 over, bracket 2 plus 1, that is 2 amperes. The terminal voltage, B equals the EMF minus IR, 6 minus 2 times 1, which is 4 volts, less than the EMF because of the internal resistance. A cross-check. Straight across R, V equals IR 2 times 2, which is also 4 volts. The two agree. The power. Delivered to R, it is I squared R, 2 squared times 2, which is 8 watts. And the maximum power transfer happens when R equals R. Now the picture of a capacitor filling and emptying, the RC curve. Charging. The charge grows as Q equals Q naught times bracket 1 minus e to the minus t over RC, fast at first, then easing up toward Q naught. The time constant, tau equals RC, and in exactly one time constant, the charge reaches 63% of its final value. Discharging. The charge falls the other way, as Q equals Q naught times e to the minus t over RC, and after 1 time constant, it has dropped to 37%. The pace, A larger R or a larger C means a slower charge. And after about 5 time constants, the capacitor is, for all purposes, completely full. Now what JEE actually asks. 5 pointers. 1. Ohm's law, V equals IR. Resistance R equals I over A. And the drift current, I equals NEA, times the drift velocity. 2. Series as the resistances, parallel as the reciprocals, and rho rises with temperature for a metal. 3. Kirchhoff, the junction rule for charge, the loop rule for energy, and mind the sign convention as you go around the loop. 4. The Wheatstone balance, P over Q equals R over S, with no galvanometer current, and the potentiometer draws no current at its null point. Number sub by itself, P equals EM, F minus I, and the time constant tau equals RC, with 63% charge in 1 tau and nearly 4 in 5. Now an assertion and reason drill. For each pair, are both true, and does the reason explain the assertion? First pair. Assertion: at the null point of a potentiometer, no current is drawn from the cell being measured. Reason: at the null point, the potentiometer's potential drop exactly balances the cell's EMF. Both are true, and the reason directly explains the assertion. The balance is precisely why no current flows. The answer is A. Second pair. Assertion: the terminal voltage of a cell is always greater than its EMF. Reason: the terminal voltage equals the EMF minus the drop across the internal resistance. The reason is true, but the assertion is false. That very drop makes the terminal voltage less than the EMF on discharge, not greater. The answer is D. Third pair. Assertion: a Wheatstone bridge is balanced when no current flows through the galvanometer. Reason: the resistance of a wire increases with its length. Both are true, but the length of a wire has nothing to do with why the bridge balances. So the reason does not explain the assertion. The answer is B. Now match each quantity to its formula. Ohm's law goes to V equals IR. The resistance of a wire goes to rho L over A. The time constant goes to RCS B. And the Wheatstone balance goes to P over Q equals R over S. 4 pairs, each worth committing to memory. Now, how many of these 3 statements are correct? 1. At the balance point of a Wheatstone bridge, the galvanometer shows no current. That is correct. 2. The terminal voltage of a discharging cell exceeds its EMF. That is wrong. It is less than the EMF. 3. In one time constant, a charging capacitor reaches 63% of its final charge. That is correct. So the answer 2 are correct. Statements 1 and 3. The trap is statement 2. A discharging cell's terminal voltage is less than its EMF. Now the 2 mistakes that quietly cost marks. The myth: the terminal voltage of a cell always equals its EMF. The truth: on load, V equals the EMF minus IR less than the EMF. They are equal only when no current is being drawn. The second myth: resistors in parallel simply add up. The truth: in parallel, the reciprocals add 1 over equals 1 over R1 plus 1 over R2, so the combined resistance is smaller than the smallest one. Now, test yourself. Answer in your head before the reveal. That is how JEE speed is built. Here we go. Question 1. 2 6 ohm resistors in parallel. 3 ohms, half of 6. Question 2. The time constant of R equals 2 ohms and C equals 3 farads. Tau equals RC, which is 6 seconds. Question 3. The terminal voltage of an EMF of 6 volts with a current of 2 amperes and R of 0.5 ohms. 6 minus 2 times 0.5, that is 5 volts. Question 4. The Wheatstone balance condition. D over Q equals R over S. And question 5. The charge after one time constant as a fraction of the final. 63%. Let us gather it all in one breath. Ohm's law, D equals IR, resistance R equals rho L, and the drift current I equals NE times the drift velocity. Series adds the resistance, parallel adds the reciprocals. Kirchhoff, the junction rule for charge, the loop rule for energy. Wheatstone, P over Q equals R over S, and the potentiometer draws no current at its null point. Nomi, cells V equals EMF minus IR, and tau equals RC, reaching 63% in one-time constant. Next class, moving charges and magnetism, the force on a moving charge and the magnetic field of a wire. A current is just electrons drifting under a push. And from that one picture come Ohm's law, the balance of a bridge, the honesty of a cell's terminal voltage, and the exponential patience of a charging capacitor. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack JEE. I will see you in the next class.